Hello everybody and welcome to the next lesson of the array chapters, which is partial sums. This is a trick that we are going to use a lot of times during coding interviews while solving challenges. It's a fundamental one, so please be attentive and make sure you understand it. We are going to start with a problem to see how this is put in practice. So the problem is the following. Let's say we own a room of servers. So each of these is a server, right? Which are indexed starting from 0. So server 0, 1, 2, and so on and so forth. And the servers are placed in a row one after another, right? From left to right. We received a lot of offers from managers, each of them wanting to buy a consecutive sequence of servers. Let's say for performance purposes, it's better to have consecutive servers, right? Just for the sake of the problem. So each of them wants to buy a consecutive sequence of them. And each server has, of course, a price associated to it. So in this example, we have the array prices, which is going to tell us how much each server costs to buy it, right? So the first one, server number 0, costs $1, let's say. The second one, $7. The third one, $2, and so on and so forth. In this example, we have 8 servers, right? So because they are busy people, our task is that for each offer, we need to answer them as quickly as possible. What is the total price of buying these servers that they desire? So you don't know how to write any code. Let's say you're just someone on the phone, like a service call guy, right? Which receives these phone calls and they are like, I want to buy all the servers starting from position 0, so server number 0, the first one, all the way to server number 4. So basically he wants to buy the first 5 servers. And we need to tell them quickly what is going to be the total cost to buy those servers, right? So that's it. Let's take a look at this example and really understand what's happening here, right? So as I've said, we have 8 servers and we are given as the input the prices array, right? With the price of each server. And we know these queries, which is basically each phone call that we get from a manager. And we have to answer them with a number representing the cost of buying all those servers. For example, the first query is 04. So as I said, he wants to buy all the servers starting from this one, the first one, all the way to the 5th one, right? On position number 4. Well, the total sum of acquiring these servers, how much is it? Is 1 plus 7 plus 2 plus 9 plus 4, right? Now let's do the math. 8, 10, 19, 23. So the answer to the first query, to the first phone call, is $23, let's say, right? Then the second manager wants to buy all the servers from server 1 to server 3. So it's this one, right? 7 plus 2 plus 9, which is a total of 18 servers. So we are going to answer him 18. The next one is 5, 5. So only this server, which has cost 5. So the answer to this query is 5. And the last query, which is 4, 7, basically the last 4 servers, right? So 4 plus 5, 9 plus 3, 12 plus other 2, 14. All right. So this is basically what we'll have to output, right? The input is the array of prices, which let's say you have as the call service operator in front of you. And each time we receive queries, so we can imagine that we receive m pairs like this of integers, which are, of course, all of them greater than or equal to 0, and all of them less than the total number of servers, so less than 8, right? Great. Now, let's see what is one solution that we can come up with here. All right. Now, of course, if we didn't know any better, one way of doing that is having the list of prices in front of us and taking each and every one server that that manager wants to acquire and adding them together, right? So what I can do is, of course, start on paper, have my paper in front of me, start with the sum 0, and then go through all the servers. Now, from 0 to 4, I take a look at server 0, the price is 1, so here it becomes 1. I took a look at the next server, 7, of course this becomes 8. Take a look at the next one, 2, of course this becomes 10. And take a final look, no, not a final look, sorry about that. Another look, 19, and then take a final look here and see, all right, those are all my servers, and I have a total of 23. So one way of doing this is actually going through all the servers in the range and adding those numbers together. So we have just come up with the first approach, which is of course a brute force approach. But what we can do here is that when trying to solve the query left-right, so computing the total cost to acquire all the servers from server number left to server number right, we can start off with a variable sum, which is initially 0, and go through each of the servers from left to right with this index I, and then increase the sum with prices of I. Obviously, in the end, we will return the sum. Now, why do I say that this is a brute force approach? Is that, of course, the time complexity of it is pretty large. How many operations do we do in this whole algorithm? Well, sum equals 0 is a constant, return sum is a constant, but we have this for loop. Inside the for loop, we only have an addition operation, which is also constant. So all we need to ask ourselves is how many iterations does the for loop do? Well, it goes through all the values from left to right. So we enter the for loop with I equals left plus 1, left plus 2, and so on and so forth until I equals right. And then when I becomes right plus 1, we exit it. So we have in total, how many? Right minus left plus 1 iterations, right? Now, let's compute the time complexity of the algorithm. Obviously, we can't express the time complexity of right minus left plus 1 because right and left are not in the input. All we know from the input is the array prices, its length, which is the number of servers, and let's denote that number of servers as n. And because we have right minus left plus 1, we need to make an upper bound of this value based on n, right? And of course, for that, we take the worst case scenario. So because right minus left plus 1 is in the worst case scenario when left equals 0 and right equals n minus 1, so we want to acquire each and every server, this one will be less than or equal to n. So in the worst case scenario, we are making n iterations for each query. So we answer each query in a total time complexity of big O of n, right? Now imagine, if you had those 10,000 servers and you are successful and you receive a lot of phone calls during the day, I don't know, let's say 100,000 phone calls or something like that. Let's say there are more people, or doesn't even matter. You're going to take a lot of time to answer all the queries. And yeah, when a large query comes, you're not going to be able to finish the day with the other calls, right? So we definitely need a better approach for this. And the better approach consists in making this time complexity of answering the query to be constant. So we want to know the answer to each query in constant time. Let's see how we can do that. One smart thing that we can do here, in order to answer these queries in constant time, is compute other information. Let's say we are going to spend a weekend to compute another array, which I named sums, which will be of length equal to the length of prices plus 1. And all of this in exchange to the fact that we are going then to be able to answer the queries way quicker. This technique, in which we spend some time or time complexity and then are able to do other tasks way quicker and the overall time complexity to be smaller in the end, is called pre-computing. As you can see, the definition of sums. Sums of I is equal to the total cost of acquiring the first I servers. Let's see what it means here. We are going to start with sums of 0, and sums of 0 will be, of course, 0 because we are not acquiring anything, right? It might seem non-intuitive at first, but trust me, we are going to use the sums of 0. Then, sums of 1 is the cost of acquiring the first server. The first server costs 1, so this is 1. Sums of 2, acquiring the first 2 servers. 1 plus 7 is 8. Sums of 3, acquiring the first 3 servers. 1 plus 7 plus 2, which is 10. Sums of 4, the sum of acquiring the first 4 servers. One thing I can do is again go through all the 4 numbers and compute their sum, but I can be smarter about this. The sum of the first 4 integers is equal to the sum of the first 3 integers plus the 4th one, right? And I think I've already computed the sum of the first 3 integers, so I compute it again. It is 10, which is sums of 3, to which I will add the 4th cost. So I get a 19. Then, following the same reasoning, 19 plus 4, I get a 23. And again, 23 plus 5, I get a 28. And again, 28 plus 3, I get a 31. And finally, the last value in sums, 31 plus 2, I get a 33. Alright, awesome. Let's check if we are correct. What's the total cost of acquiring all the servers? Well, it's 1 plus 7 plus 2, this is 10, 19, 23, 28, 41, 43. Awesome, indeed correct. So again, we are computing the sums array, right? Where sums of I is the total cost of acquiring the first I servers. And now the question is, how are we going to use this new array to answer our queries? Let's take as an example the query 2, 4, where we basically have to compute prices of 2 plus prices of 3 plus prices of 4. How can we express this sum as the difference of 2 values in the sums array? Well, it actually is pretty simple, but we'll have to do a trick here. We can write prices of 2 plus prices of 3 plus prices of 4 as prices of 0 plus prices of 1 plus prices of 2 plus prices of 3 plus prices of 4 minus the first 2 that we've just added, right? Prices of 0 plus prices of 1. And how is this going to help us, Andy? Well, don't you see the pattern? Prices of 0 plus 1 plus 2 plus 3 plus 4 is the total cost of acquiring the first 5 servers. So I can write this with sums of 5. Prices of 0 plus prices of 1 is actually the total cost of acquiring the first 2 servers, right? So I can write this of sums of 2. So look how simple. We've just come up with the formula sums of 5 minus sums of 2. On a visual level, you can imagine that the sum of this subarray is actually equal to the sum of this greater subarray from which we will have to remove the sum of this subarray, right? So we are basically taking the sum of the first servers from server number 0 to server number right and remove the sum of the first server starting from server number 0 and all the way to server number 1, right? This is exactly why we have here sums of 5, because we will take the first right plus 1 servers, because between server 0 and server right, there are a total of right plus 1 servers. So sums of 5 minus the first left servers, because between server number 0 and server number left minus 1, we have a total of left servers. And this is exactly how we do this. And the beauty of this is that we can do this for a subarray or a subsequent of consecutive servers that has thousands of servers. It doesn't matter. All these thousands of additions will just get translated into one difference. So let's verify it. What is sums of 5? 0, 1, 2, 3, 4, 5. It's 23. Minus, what is sums of 2? 0, 1, 2 is 8. 23 minus 8 is 15, which is indeed our sum, 2 plus 9 plus 4, right? If we take yet another example, let's say query of 3 and 6. This is prices of 3 plus prices of 4 plus prices of 5 plus prices of 6. This one also, like we did with the previous one, can be written as prices of 0 plus prices of 1 plus ... plus prices of 6. And then decrease with prices of 0 plus prices of 1 plus ... oh, no, it's only by prices of 2. All right. And again, this one is the sum of the first 7 servers, right? So from 0 to 6, we have 7 servers. Be careful here. And this is the sum of the first 3 servers, right? So sums of 7 minus sums of 3. So we have yet again sums of right plus 1 minus sums of left. Awesome. Perfect. Let's also see it visually. From 3 to 6, we have this subarray of prices, which can be written as the subarray consisting of the first 7 servers, which starts here and goes all the way to here, from which we should remove the subarray consisting of the first 3 servers, which starts, of course, here and go all the way through here. Remove this one from the bigger one, and we have our subarray. Sums of 7 is, let's see, 31. Sums of 3 is, let's see, 10. 31 minus 10 is 21. 9 plus 4 plus 5 plus 3 is also 21. So I think we just came up with our solution. Awesome. And here it is. All we have to do to answer the query left-right is just return sums of right plus 1 minus sums of left. And of course, because we will have the sums array pre-computed, the cost of just returning this difference is constant. So now we are able to answer those questions very, very quick. Again, with the cost, paying the cost of first taking the time to computing sums. And let's see how much time it actually takes to do that. Now, the basic way of doing this is, first of all, make sure that sums of 0 equals 0, because none of the elements in prices will actually be present in that sum. Then, for each I between 1 and n, we want to compute sums of I. Sums of I being equal to the sum of the first I elements, we can just iterate through them, right? So for each index j between 0 and I minus 1, just increase that prices of j to sums of I. Now, obviously, we do this supposing that the array sums is already filled with zeros, right? So yeah, indeed, we can comment this. We won't necessarily need this initialization, but just make sure that the array sums is filled with 0. And yeah, basically that's it. But there is one problem. And the problem is that it will take a very long time to do that. Again, let's suppose you have 10,000 servers. Let's find out how many additions like this you'll have to make in order to compute every element in sums. We obviously have two nested for loops. So in order to analyze the time complexity or the number of operations, we will start from the inner one. And let's see. This for loop has only one addition here, which is of course a constant operation. And how many iterations does the for loop do? Well, it takes each value starting from 0 all the way to I-1, assign it to j, and then get inside. So j equals 0, j equals 1, dot, 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 j equals I-1. This is a total of I operations. So for each value of I, each time we enter this for loop with a different value of I, we are making that number of operations, right? So let's see. First, I is equal to 1. So when I is equal to 1, we'll have for each j starting from 0, ending at 0. One operation, right? So we have here a 1. Plus, in the next time we enter the for loop, I equals 2. For each j from 0 to 1, this is a total of 2 operations. Next time we enter with I equals 3. So a total of 3 operations inside the inner loop. And so on and so forth. The last time we enter the first for loop is with I equals n, and we are making a total of n operations, so plus n. Now, we have to compute this sum in order to know what is the number of total operations our algorithm does. As you probably know, this is a Gauss sum. If you don't know, don't worry about it, just Google it. The point is that we have a formula for this, which is n crossed n plus 1 divided by 2, right? So, this is the total number of operations or of additions that your program, or in our problem ourselves, have to do. For n equals 10,000, that's a lot, right? Obviously, the time complexity of computing these partial sums is 1 of big O of n squared, right? Because we don't take into account the constants. Well, it is a pity, because optimizing our solution such that we answer those queries very quick in constant time would be in vain if we actually don't have the physical time to do this many operations, right? Let's suppose you have 10,000, 100,000 servers. You won't be able physically, or you'll quit to compute all those sums, right? So we need to also be realistic on this one. Let's compute these partial sums in a total time complexity that, of course, won't be constant, because you need to compute n elements. I mean, you can't compute n elements in constant time, all of them, right? But in total, compute each element, each of them in constant time, and because there are n elements, let's have a time complexity of a total of big O of n. And let's see how to do that. Actually, I gave you a hint earlier when we were computing these sums here. Can you remember? When I had to compute, let's say, sums of 3, so the sum of the first 3 prices, I've said something like, I mean, not on this one, I think on the 4th one, to be more specific. Anyways, alright. When I had to compute the sum of the first 4 prices, I said something like this. I don't want to go again through all those 4 prices and add them together. What I can do is notice that the sum of these 4 elements is actually equal to the sum of the first 3 elements which I've just computed plus the new one, right? So all I need to do is take a look on the previous, on the previous element, which is 10, and add the new one, which is 9. 10 plus 9 is 19. Let's take, for example, this 41. In order to have the sum of all these elements, I think there are the first 6 elements, I need the sum of the first 5 elements, which is 28, plus the new one, which is 3. And that's how I got the 31, right? So, in more, let's say, mathematical terms, let me erase this for a bit. In more mathematical terms, I can say one thing. I can say that sums of I, which is the sum of the first I elements, which is prices of 0 plus prices of 1 plus plus prices of I minus 2 plus prices of I minus 1. This one is actually equal to, let's group the first elements together. So from prices of 0 all the way to prices of I minus 2. And I already know this sum, because this is obviously the sum of the first I minus 1 integers. So instead of this, which is a total of I minus 1 additions, I only can write this, which is, of course, getting one value. And this is constant, right? So, supposing that, this is very important, supposing that when I want to compute sums of I've already computed sums of I minus 1, I take that value and increase it by prices of I minus 1. And this actually happens, because let's take a look at the order in which we compute the sums. We compute them increasingly. I mean, first sums of 0, then sums of 1, then sums of 2, then sums of 3. So when I want to compute sums of, let's say, 10, I've computed at the previous step sums of 9. So I know that value. This is awesome. What I can do here is the following thing. I can write this. Sums of I is just equal to sums of I minus 1 plus prices of I minus 1. All right. Let me erase this so you can see. Okay, great. And this is the formula, right? Now we can remove this. And yeah, awesome. And that's it. Again, supposing that sums is already filled with zeros. I mean, now it doesn't necessarily have to be filled with zeros, because we just assign a value to it, right? We don't suppose it's initialized with something or stuff like that, but make sure that sums of 0 is 0, at least that one should be, right? So if I were to move this a little bit here, one more thing that I'd like to add is that sums of 0 will be equal to 0, right? And this is it. Awesome. Now let's take a look at this one. All I do here is initializing sums of 0 with 0, and then for each of the n steps, or the n times I enter the loop, I just make an addition, which is constant time. So now we are computing this sums array in a total time complexity, let me write it, of big O of n. And this is awesome. So now, even if the servers, I mean, there are a lot of them, it is more humanly to compute all those sums, right? So if we were to analyze the total time complexity of this algorithm, what we would come up with is the following thing. We have step number 1, which is, as I called it, the pre-computation, which takes big O of n, time and memory, because we need an extra array sums, and we take big O of n to compute it. And then the second step, which is answering the queries, right? Answering queries is big O of 1 per query, time complexity. And this is what the partial sums are about. So obviously our example wasn't like one that you will use in your day-to-day software engineering job, but let's suppose that you have a server and you have to write a feature that takes something like 100,000 queries or requests per second, and you need to quickly answer all of those with the sum of some subarrays or some consecutive numbers in a list, right? Then definitely you are going to use the partial sums, right? There's no way of answering 100,000 of those queries by just iterating through 1 million numbers or stuff like that, right? We are going to use this trick a lot, not only when computing the sum of some subarray, but also when trying to find out some specific subarrays. We're going to see on the future problems, maybe how many subarrays have a specific sum, or maybe what is the greatest sum of a subarray of a given length, and a lot of other problems. This was it, guys. Enjoy the coding and see you on the next one. Bye.